Hi, physics. Mr. Janowski here. This is Chapter 9, Homework 3, and I'm going to do problems 3 and 4, which are related. So let's see what's going on. We've got Charlie, who's got a mass of 62.5 kilograms. He goes down a slide that is not frictionless. The vertical drop of the slide is 2.00 meters. If he starts from rest and reaches the bottom traveling at 5.25 meters per second, how much work did friction do? And there's our answer. So let's see how we're going to do this one. First, of course, step So what are we looking for and what units do we expect it to have? The question is, how much work did friction do? So work from friction, call it W sub F. This is equal to question mark, and it's work, so it's going to have units of joules. Remember that work and energy both have units of joules. So now we do step 1, which is make a sketch. But because this is a conservation law, we're going to actually make 2 sketches. So our initial sketch, we've got a slide. So imagine those are the steps. And it goes down like this. We have Charlie sitting at the top. So here's Charlie. He's got a mass of 62.5 kilograms. The vertical drop of the slide is 2 meters. So he's going to change heights in this problem. He's going to go from up here, the high height, to he's going to end up down here. So let's call the initial height 2 meters. H sub I is 2.00 meters. He's going to go down here. There's going to be friction, and he's going to end up going that fast at the end. All right, so anyhow, this is our initial one. Final sketch. So there's the ground. All right, that's close enough to being the same slide. At the end of the problem, Charlie's moving like this, and he is moving, so we're giving him speed lines. He's going in this direction. His final velocity, V final, is equal to 5.25 meters per second. And I guess if I wanted to specify, I could say up here that his initial velocity was 0. So you don't have to write this out explicitly, but he's not moving at the beginning. He starts at rest. So V initial is 0 meters per second. So there's our step 1, 2 sketches. Now we do step 2, which is the law of conservation of momentum. So sigma E initial plus sigma work external is equal to sigma E final. So take it term by term. Sigma E initial. Look at your initial sketch. Ask 3 questions. First of all, is it moving? Nope, he's not moving. Is it at a height greater than 0? It is. We're starting up here. I forgot to mention that in the bottom sketch. All right, just to be thorough, down here, H final is 0 meters. But anyhow, in the initial sketch, not moving, no kinetic energy. Is it at a height greater than 0? It is. We're at a height of 2 meters. So that means we have GPE initial to worry about. And then the last question is there a spring that is extended or compressed? Nope, there's no spring in this problem at all. So there's no EPE to worry about. So the first term, sigma E initial, sum of the initial energies, well, there's only one initial energy. There's only GPE initial. Second thing, sigma work external. Is there anything outside of our system that's giving us energy or taking energy away from us? And the answer is yes. That's what we're looking for. There's work being done by friction. This is not a frictionless slide. So therefore, we're going to have this term plus W sub F, work being done by friction. And that's the only kind of external work we've got. And this is equal to sigma E final, the sum of your final energies. So look at your final sketch and ask 3 questions. First of all, is it moving? Yes, it's moving. There are speed lines. So we do have KE final. Next question, is it at a height greater than 0? Nope, at the end, it's at a height of 0. So there's no GPE final. And then the last one is the one about the spring. Well, there's no spring. So there's nothing to worry about there. So our law of conservation of energy, this universal truth up here. When we apply it to this particular situation, this is what we get. GPE initial plus work due to friction is equal to KE final. Grab the green pen and do step 3, which is math. So GPE initial, I'm just going to turn the things into the things. That is MGH initial, because here's my formula for GPE, plus work due to friction. Well, this is what we're looking for, so I'm not going to turn this into the work formula. That'll be problem 4. But the work due to friction is just going to stay work due to friction. And then the last term, KE final. Well, here's our formula for KE. So this is equal to 1/2 m v final squared. So 3 terms here. The one we're looking for is v final. So to get that by itself, we've got to subtract mgh initial from both sides. Once we do that, we end up with work final is equal to 1/2 mv final squared minus mgh initial. All right. So, I mean, if you want, you can factor out the m. You can't cancel it because we need it. Like, we're not dividing work by mass. You could factor it out and like write it like this: v final squared minus gh initial. There's no point to doing it that way, though. Just plug in the numbers, see what you get. So let me back up a little bit in case I run out of room. Work final is equal to 1/2 times m. M is 62.5 kilograms. Times v final squared. Okay, v final is 5.25 meters per second. That gets squared. I realize that looks halfway between a 5 and a 3, maybe. Let me write that just a little bit nicer. Is that nicer? It'll have to do. So yeah, that's that first term, minus m, 62.5 kilograms, times little g, which is 9.8 meters per second squared, times h initial, which is 2 meters. All right. Do all this work in the calculator. That's a terrible W. All right, there we go. So 0.5, 1/2 times 62.5 times 5.25 squared minus 62.5 times 9.8 times 2.00. And we end up with work final is equal to minus, I get 363.67, yada, yada, yada. It's work, so it's joules. So let's call it minus 364 joules. If we're keeping 3 sig figs, that's what we get. That's the work due to friction. All right, grab the red pen. Do step, We wanted work done by friction in units of joules. We have work done by friction in units of joules. It's negative. Does that make sense? Yes, it does make sense. Friction will do negative work. So we're happy with that. We give it a check. So there's our answer for problem 3. Now, problem 4 is a continuation of this story. So Charlie goes down the slide. Friction does that much work. If the length of the slide, not the vertical drop, is 4.00 meters, what was the magnitude of the force due to friction? So the vertical drop was 2 meters. What I'm saying here is that, let me draw it up here. This length here, let's call it d for distance or displacement. This is 4.00 meters. And we're trying to figure out the magnitude of the force due to friction. So if we're going to do step what we want is the magnitude, so absolute values. F sub k, it's kinetic friction because he's moving. In the absolute value signs, because we just want the magnitude, the positive number, we don't care about the direction. This is equal to question mark, and what units will it have? Well, it's a force, so it's going to have units of newtons. So we've got to figure that one out. So in this problem, I'm not going to do it the whole big strategy way. What's going on here is we want this force here. The things we know are the amount of work that's done on him, and we know the displacement. Charlie going from here down to here goes 4 meters. That much work is done on him, and we need the displacement. So for this one, we're going to just be using this formula. Work is equal to magnitude of the force, well, it's the force due to friction, times his displacement, or the magnitude of his displacement, the distance, times cosine of theta, the angle between them. So what's the angle between them? All right, well, if Charlie's going down this slide like this, let me change colors. Maybe we can see this a little bit better. Charlie's going to go down this slide this way. So if I'm going to draw his displacement vector, it's something like this. So that's our d is equal to 4.00 meters. Now, which way is the force going? Remember, friction opposes the motion. So if Charlie's going this way, the force due to friction he's getting is going to be in exactly the opposite direction. It's going to be up like that. So F sub k is going that way. And what's the angle between them? The angle from here to here, well, the angle of anything in the opposite direction, is 180 degrees. So theta is 180 degrees. So where were we? We had this formula. We're trying to solve for F sub k. So to get F sub k by itself, we're going to divide both sides by the magnitude of d times cosine of theta. So divide this guy over here by the magnitude of d times cosine of theta. Magnitude of d cancels on the right. Cosine of theta cancels on the right. And what we're going to end up with is, and I'm switching left and right here, the magnitude of the force due to friction, the magnitude of F sub k, is equal to the work that is done times the magnitude of the displacement times cosine of theta. All right, so we've done everything. We've just got to put in the numbers now. So the work that is done, well, that's negative 364 joules. The magnitude of the displacement, he has gone 4 meters. So that is 4.00 meters times cosine of theta. Well, what is theta? Theta is 180 degrees. Cosine of 180 degrees ends up being negative 1. So if you do this in the calculator, take minus 364, divide by 4.00, and divide by cosine of 180. And you end up with positive 91. And if we're keeping 3 sig figs, it should really be 91.0. It's a force, so it's going to have units of newtons. Put a box around it. Grab your red pen. We wanted the magnitude of the force in units of newtons. We have the magnitude of the force in units of newtons. Is 91 a sensible number of newtons for a force due to friction? Yes, that makes sense. That's a reasonable number. So we're happy with that. We give it a check. So hopefully you found that helpful.